Welcome back. So this is the last and the final topic in this course, and I'll be introducing it to you for the first time, and this is called initial access. Okay, we'll discuss what initial access means, and then I'll only be able to teach you a part of it very briefly. Okay, initial access involves few more steps than what we will be able to cover in this class. Okay, but it will give you an idea of the kind of challenges which are there in this initial access problem. Okay, I'll have to define it for you. What does that initial access means? Okay, so first of all, we'll define this initial access problem for 5G NR. Okay, for FR1 and FR2 system. See, this initial access problem, once I tell it to you, you will be able to appreciate that this is a common communication problem. Okay, it is. And any communication problem between a transmitter and a receiver is bound to face this. Okay, whether it's between your TV satellite and your dish antenna. Okay, a normal simple communication system point to point to transmit from point A to point B. Okay, so this initial access problem is going to be there. Okay, once you walk through this, you'll be able to appreciate. Okay. But what is, in context of 5G, what this initial access is, basically, what are we saying? Look at this bullet. When user is trying to enter a network, okay, it does not have any information about the base station. What do I mean by user is trying to enter a network? Let's say you bought a new mobile, okay, right, and you're switching it on, correct? Okay, so this your mobile station does not have any particular notion of what a slot boundary is, what a frame boundary is. Okay, right? It will know that okay, that slot is 0.5 millisecond because it is programmed, but it will not be synchronized to the base station. Wherein base station will have its own definition of 0.5 millisecond. Okay, right? It's like you buy a new watch. Okay, right? You will have to align it to some common definition of the time, right? Okay, because the watch did not have a battery inside, and then you are bringing it to life. Then you'll have to synchronize this to Indian Standard Time. There's something of that sort. Okay, you switch on your mobile, you'll have to synchronize it to your time to the base station. Okay, so that both of you have the same notion of time. Okay, right? And that is a problem with any receiver. Okay. Now, when you have the cellular network, this problem becomes more severe because you move on from one cell to another. Correct? Okay, right? And then that base station, another base station. Okay, if they are synchronized to each other, it's okay. If they are not synchronized to each other, then you will have to use this synchronized to other base station. Okay, right? So this is basically the problem which we are talking about. So what are we saying? It does not have any information about the base station, not even the timing. Okay, but other information, as I said, right, where the control information is being transmitted. Right? Okay. So all that information, basically a user tries to get during the initial access. Okay. Now base station also does not have any information about the user. Correct? Okay. Right? Just for example, its channel, its uplink channel. Correct? How far this base station user is from the base station so that it can tell the user to transmit at a particular power. Right? Just for example, I am considering very familiar examples. If the user is located far from the base station, the user will have to transmit at a higher power. If the user is located close to the base station, user will have to transmit at a lower power. Base station doesn't know all that. Okay, that's also part of initial access. Broadly, multiple such things happen, but I'm giving you immediate examples which you can connect to. Okay, so initial access is a broad term. It is basically used to acquire this knowledge. Okay, right? And this is few aspects of this knowledge. There are multiple such other aspects, but if we understand how this is happening, it's good. Okay, it's enough for this course. Okay. So initial access is basically acquisition of this knowledge, and it's divided into uplink and downlink synchronization. I'll define what does that mean, okay? So then there are this different initial access strategies for FR1 and FR2, okay? I'll briefly be able to tell you that, okay? So we'll look at all that, okay? So we'll first look at the steps which are common to FR1 and FR2 initial access, okay? So what I've done here is I've taken some, and this is slightly old figure, okay? So what is this? I've taken the slot boundary to be 1 millisecond, okay? Can be 0.5 millisecond and can be, right? So it is like for 30 kilohertz it's 0.5 millisecond, but I've taken this like, as a 1 millisecond. Now this is a user, this base station, okay? So as I said, if a user switches on, okay, right, what will happen? It will have its own definition of 1 millisecond. Correct? It switches on at this time, it doesn't know what is happening, it just switches on itself. Correct? Okay? Right? So, and base station is transmitted according to its own definition. This is its T0. It starts its time from here and then starts transmitting. This is the first symbol, second symbol, third symbol. Let's say this is for 15 kilohertz. The slot duration is 1 millisecond. Okay? Old figure. If it is 30 kilohertz, it will be 0.5 millisecond. That's all. Okay? What are we saying? At time 0, the base station will transmit symbol 0, then symbol 1, symbol 2. User is basically switching on at some time, okay? For the first time when it switches on here. You see this is basically, the duration will be same. This clock duration, what I'm saying, okay? Slot duration will be same, okay? But where it is switching on, right? That is completely offset. This is 0 and user will say this is its 0. Correct? It's like you basically enable your watch initially, like if it is like you set it up at 1 o'clock instead of 12 o'clock, but the actual time is 12 o'clock. We are offset by an hour. Right? In your mind, right, you would have basically like the time, there is a time difference, but your mind doesn't know. Okay? That what am I saying here? That user will think that this is time 0, but base station time 0 is this. It will start collecting samples, base station is transmitting, user will start collecting data according to like this. Right? Okay? Fine. Then this is our received OFDM slot. Okay? This you can subframe, you can read as slot. Okay? And just for this is basically you can write this as slot. Okay? Right? What happens? User misses this. Okay? Right? And that's a wrong reception. And where is this happening? This is happening in the downlink. Okay, how will a user ever be able to receive data if this is what is happening? Correct? Okay, because user will always think that this is T0, base station will always think that this is, but base station doesn't change, base station will always keep transmitting at its own T equal to 0. Right? Okay? So and this is, as I said, this is a common problem for any communication system. So user basically has to figure out that this is the gap between its T0 and base station T0. Okay? Right? And then it will basically be able to tell that it will be able to correct it. Okay, it will basically align its boundary to this T equal to 0 if it knows this gap. Okay, so a user has to know this gap wherein so that it can align appropriately. How does that happen? Okay, right? And I'll give you a recipe of doing that very briefly, but we'll show you how that happens. Okay, right? You understand? You are able to appreciate this problem that there is this gap. Okay, and which needs to be corrected so that this boundary could be aligned, and then user can collect all the data. Right? Once it has the complete data, then only it can form a grid. Right? And then only it can it can find out, it can do this blind decoding. But before that, it cannot even do that. Okay? Right? So what happens? That user acquires this subframe or the slot boundaries. Okay? Right? Basically aligning it to this. Okay. Once it has this it aligns it like this, it will know that okay, this is symbol 0, this is symbol 1, and then it can start processing its data. Okay, right? So, and then another part of it, which I will not be able to touch upon, that these two base station and user, okay, they have their own notion of frequency also. What is this frequency? This frequency, the RF frequency to which we upconvert, okay, right? So base station will upconvert it to, when both of them are upconverting into like say 2 gigahertz, okay, but there will be some offset, okay, between base station and user. So it will be 2 gigahertz, but it will be, this will be 1.999 gigahertz, okay, that 0.001, that gigahertz, it actually needs to be corrected by the user, okay. That also is a part of the initial access. So that this problem needs to be solved by the user, and it's a well-studied problem. People know that. That's how our mobiles are working. Okay, right? So now this is downlink synchronization. Okay, the user does that, and it basically finds out that its boundaries are offset. Okay, it aligns this, right? Okay, it aligns the boundary. Now, once it has finished this, there is next step of it, which is called the uplink synchronization. Okay. And what is this uplink synchronization? That's what I'm going to describe. So what is, once user completes downlink synchronization, it has to synchronize in the uplink also. What is this? Let's see that. Okay. So let's say these all three users, okay, have synchronized in the downlink. Okay, they're trying to enter the network. Okay, but they have done the synchronization. Okay, correct. Now, this user basically is the closest to the user, to the base station, and this user is farthest from the base station. Okay. Now, what is this RTD? This is round trip delay. Okay, correct. Now, base station will transmit the signal, user will receive it. Okay, user will receive it with some delay, right? Okay. Now, and this delay will be smallest for this user and largest for this user. Correct. We understand that. Okay. Now, it's fine in the downlink. It is fine. Each one of them receives it with delay. Now, when these users try to transmit data in the uplink, okay, right? What will happen? This user's data will reach at the earliest. Okay, and this user data will reach after that. So this is a problem. Okay, right? Here also you can basically read this as subframe as slot duration. Okay, correct. Okay. Now what will happen here is, this is a base station timing reference, t is equal to 0. All of them are synchronized in the downlink. Okay, it doesn't matter whatever delay they are observing. Correct. They have aligned their t is equal to 0. Okay, with the base station t is equal to 0. But what will happen? There will be some delay, right? Okay. Because then, of course, and that delay is the flight delay between the transmitter and the receiver. Okay. Now, when the user 1 transmits, okay, correct, okay, what will happen? Because of this delay, it will not, whatever symbol it has transmitted, okay, it will reach at the earliest. This green one is reaching at the earliest. The black one is reaching with more delay, and then the orange one is reaching with the maximum delay. But what is this delay between this user and this user? What's happening? Okay, because what happens, you look at this, let's go back to understand this, right? So there is this, our downlink synchronization. Okay, now base station transmitted this, okay, correct. Let's say user has what will happen to this signal? User will receive it with some delay, right? Because that's the flight delay. Okay, so now what will happen? This base station transmits this. Let's say downlink synchronization is done. Okay, that's okay. It has somehow been done. What am I saying here? So this is the actual symbol of the slot. Okay. Now due to this flight time, what will happen? This user, the closest user, will receive this entire frame with certain delay. I'm talking about this delay. Well, this is a flight delay. Base station transmits it. The signal takes some time to reach the user. Okay. So user timing definition in the downlink will be according to whatever signal it is receiving. Okay. So its timing definition will start from here. Once it is synchronized in the downlink, I'm not talking about this phase, okay? In this phase, there is this problem, right? So it's synchronized in the downlink. What will happen? Its definition of this slot will start from here with certain delay. This is what it is. I'm talking about this delay. This will be its definition of 1 millisecond, but it's fine because the signal is being received with this delay, right? Correct? Because that's the time it takes from the signal to reach from transmitter to receiver. Now with this delay, user will transmit the signal in the uplink, right? And it will become twice that delay because this is in the downlink and the same delay will get added in the uplink also, okay? So this is what it will become, this is that delay I'm talking about, okay? In the downlink it is fine, but in the uplink, all these signals should reach in this, the definition of 1 millisecond of the base station, correct? Otherwise, base station, how will base station know? Base station will not be able to collect all these signals, right? Okay, because they are delayed. But in the downlink it doesn't matter because each user cares about its own boundary, okay, of 1 millisecond. But in the uplink, because of this delay, right, this plus one more time that delay comes, this is called round trip delay, okay? And this round trip delay will be largest for this user, correct? Okay, so what is each of the user in the downlink will have to do timing advance, okay, right? And what is this timing advance? Whatever is delay they are observing in the downlink, okay? But in the downlink everything is correct for the user, okay, right? Base station will tell somehow, there are like, that's what is the part of uplink synchronization, okay? Some special sequences are transmitted in the uplink, okay, which will help the base station in figuring out this delay, okay? And that delay is basically indicated to the user that it should advance its time by this much so that it reaches, this slot reaches in time. This will be the delay for the user 2, this will be the delay for user 3. That base station calculates and tell the user that please advance your transmission, okay, right? So that advancing means what? So that you can basically, whenever this uplink begins, right, according to the definition t is equal to, let's say, 0.5, okay, it's beginning at some t is equal to t uplink, okay, it'll start transmitting with some little bit in advance so that all of them reach at the same time, okay, right? And these signals, there are multiple users, right? They'll get added on air and all of them will be received simultaneously, right? And base station will take the, it will sample these signals, take the FFT, and if these signals are properly aligned, then only what will happen is resource, it can figure out resource block 1 belongs to this user, resource block 2 belongs to this user, and resource block 3 belongs to this user. Otherwise, all this is, uplink will never happen. Okay, that's the fundamental thing which is done before any other thing, whatever we have learned, can be done. Okay, right? So downlink synchronization and then the uplink synchronization. Okay, right? So this is the problem. So different round trip delays will lead to interference at the base station because they are not properly aligned. The interference means that the resource grid or the resource element at the base station will not be properly aligned. Okay, they'll interfere with each other, and that's the problem. Okay, right? So uplink synchronization involves this timing advance and then the power adjustment, because look at this. If all of them transmit at the same power, the transmission of this user will sync the transmission of this user, because this user signal will be received at much more higher power than this user. Okay, so base station will tell either to tell this user to reduce the power and increase the power of this. So broadly this is done during the uplink and this uplink synchronization. Okay, right? So these are the problems. Okay, how is it done? I'll not be able to cover this uplink synchronization, but I'll be able to briefly tell you about how downlink synchronization is done. Okay, so in order to help the user synchronize and downlink, base station periodically broadcasts something called synchronization signal, SS, to help users synchronize in the downlink. Okay, what are this? So synchronization signal, they are called SS. Okay, SS blocked, SSB, okay, are transmitted in a block which consists of primary synchronization signal and secondary synchronization signal. Okay, and there is something called physical broadcast channel. Okay, so the SS block consists of these signals. Okay, and what are this? You look at this, where are they coming? Okay, there is this primary synchronization signals which is sent over 127 subcarriers. Okay, it's a code. Okay, then there is this physical broadcast channel. The broadcast channel, like what other channels we have studied? PDSCH, PDCCH. Okay, physical downlink shared channel, physical downlink control channel. Correct. This is broadcast because this information, this is a system information which is broadcasted to all the users. Okay, so users should first find out the slot boundary. Okay, perform frequency offset estimation using these signals, primary synchronization signals and secondary synchronization signal. And then once they know this, that this is basically the symbol boundary. Okay, from the slot boundary, they'll be able to find out what is the symbol boundary. Then they can read these signals, PBCH. Okay, this is basically told to the user that this is a structure of one SS block. Okay, if it finds out where PSS is, it can find out where SSS is, and then it can find out PBCH information, which is coming all over here. This with this, it will be able to do part of the network entry. It contains a lot of information. Okay, right? So just to give you that, like in some part of it, like that core set, as I said, there is a common core set, right? There is user specific core set. The common core set information comes in one of these blocks. Okay, right? So this is what it is. Okay, and then there are two synchronization blocks contained in one slot. Okay, they come like this. I'm just telling you so this is one. Look at this. How many symbols it is coming? 1, 2, 3, 4 symbols, right? Okay, so this first symbol, this second symbol, so it comes in 3rd, 4th, 5th, 6th. Okay, and then the second one comes 9th, 10th, 11th, and 12th. And they don't come in every slot. Okay, right? They come with a certain period. Okay? And whenever they come, they'll come like this. Okay, right? And that period is fixed. Whenever they come. Okay, right? So that's where. So this is basically. So these are the SS blocks. Okay, SS block consists of this primary synchronization signal, secondary synchronization signal, and the physical broadcast channel. Okay, right? So what is PSS? PSS is the first signal that a user entering the system will search for. Okay, right? And you see this, that user is not even aware of its slot boundaries, right? Okay, so it should have excellent correlation properties. Okay, which it should be able to help the user to figure out. The first thing is the slot boundary. Okay, right? So user has no knowledge of the slot boundary, frame, then frequency offset. They have frequency offsets also. Okay, all this has to be corrected using this. Okay, so they are well-designed sequences which helps the user in basically downlink synchronizing. Okay, right? So PSS, primary synchronization signal, has been designed to be detectable despite these uncertainties. Look at the problem. And user has to detect this PSS, then only it can enter the network. And they have been designed very carefully, right? So that the user can detect them despite there are these, like it doesn't know the frame boundary, it doesn't know the frequency offset. Okay, and they are called, so the PSS, the 127 length, you see this. Okay, that's why this 127 length. It's a 127 length M sequences that are like Z of shoe sequences. There are other kind of sequences which have excellent correlation properties. Okay, user will be able to detect them with these uncertainties. And there are 3 different PSS sequences. Okay, so this basically these 3 different PSS sequences because there are different base stations. Okay, in a cell. Okay, and each cell has a different base station. Okay, so each cell has an identity. Okay, so each of this basically cell will be using one of these PS sequence. Okay, let's say you have a cell. Okay, each cell will have 3 sectors. Okay, right? So first sector will use one PSS sequence, second sector will use second PS sequence, third sector will use third PS sequence. Okay, so that they don't interfere with each other. Okay, then SSS is again 127M sequence, and there are a total of 336 sequence. So you see these sequences are used across different sectors in different cells. Okay, primarily so that they don't interfere with each other. You see this, if they start interfering, user doesn't even know which base station it has to get synchronized to. Okay, so that's the purpose. That's why there are so many of them defined. Okay, right? So this is some bit about PSS. This is some bit about SSS. Okay, then what is contained as this PBCH. It contains system frame number. Okay, it has to first find out what is the definition of a frame. Okay, what is the frame boundary? From there it has to find out the slot boundary. Okay, then there is something just to tell you, there is something called cell barred flag. If the cell is down for some reason due to maintenance, so it will be clear that okay, user will not get locked to this particular cell. Just to tell you that this kind of information comes in this broadcast channel. Okay, right? So as I said, base station periodically broadcasts the synchronization signal to help user synchronize in the downlink. Now see this, it cannot perform any user specific precoding because they are broadcast signals. You cannot align them, you cannot precode them for a particular user. Correct? Because whatever we have learned till now, okay, in this fully digital architecture or other, always you precode with respect to specific user. But look at this information. This is meant for all the users. Correct? And right, so you cannot precode them with respect to a particular user precoder. Okay? And by the way, base station doesn't even know that user has entered the network. How will it have its channel information? So this is basically, this user specific precoding is not done on this. There's something called broadcast precoder. Okay, that I'll show you. Okay, so what happens here? Okay, so now I showed you this pattern yesterday. If there is one antenna, right? What are we saying here? That they are like, you need to broadcast these signals. Okay, now if there is one antenna in the system, the signal gets broadcasted. We saw that. It's only for one antenna. Right? Forget the gain. I'm not talking about the gain. I'm saying that if there is one antenna, there is the system, basically the signal transmitted from that antenna gets broadcasted in all the directions. Okay? Right? And I showed you this figure after this. Okay? Wherein I said this is for one antenna. We have two antennas, you precode them. Okay? Precode them with some general information. What happens? It is getting aligned in a signal is being transmitted in a particular direction. What happens if there are 64 antennas? Right? You have basically a very sharp beam, okay? But you want this signal to get broadcasted, not to have a system, not have a signal like this, because then a user over here will not be able to see the signal. Correct? And I said I gave you this example earlier in context of millimeter wave systems, right? That for millimeter wave system you would want this, okay? But for FR1 systems, okay, for broadcast signals, you would want this kind of behavior, right? Okay, wherein like you want this user located here should be able to receive this signal, user located here should be able to receive this signal, okay? Right? So at least for FR1 you want this to broadcast it. Okay? Right? So that's what is the difference between, I said the synchronization difference between FR1 and FR2. Correct? Okay? FR1 you want this, FR2 you would want this, but then there is a problem. A user located here will not be able to see this broadcast signal. Correct? Okay, so different kind of challenges. Right? Okay? Correct? So that's what I said, like FR1, basically, this kind of broadcast if you do, you can do it from a single antenna. If you do this, you get a beam like this, which is not favorable. In FR2, you want this kind of beam, okay? Right? But a user located here will not be able to receive the signal. How do you solve this problem? Okay? First part of it, I'll show you in this class, okay? So If BS uses one antenna, it will automatically create broad beam to broadcast synchronization signal. That's what I just said. Okay, this one. Okay, now, so what happens if base station uses one antenna, right? Then what happens? Okay, so if the systems are designed, okay, such that there is a constraint on the total transmit power. Okay, now if the base station is transmitting at 64 watts, okay, each antenna can transmit at 1 watt. Okay, right? So if you use one antenna to create broad beam, you are transmitting only at 1 watt of power, right? And then the broadcast signal will not be able to reach the users because you are transmitting with very, very low power. Okay, but if you transmit with multiple antennas, then it becomes a sharp beam, right? Okay, you don't want that also, correct? I'm talking in context of FR1, right? Okay, that you don't want this also to happen. So how do you handle this? Okay, so I'm taking an example to like explain this problem. Base station is supposed to radiate at 2 watt and has 2 antennas. Each one of the antenna will be 61 watt, right? Now if we use single antenna for created broad beam, base station coverage is going to reduce, right? Okay, so, and that's where I leave it to you to figure out. This is the reference, that special algorithms are designed to create these broad beams using multiple antennas to increase this transmit power. If you do simple precoding, right, maximum ratio transmission kind of precoding, you will form a very narrow beam. Okay, now there are these special algorithms which tell you how to create these broad beams using multiple antennas so that you can increase the power. You are using all the antennas to create a broad beam. Okay, right? And if you are using all the antennas to create a broad beam, you will use all the power. Correct? If you use only one antenna to create a broad beam, you will use only power of one antenna, which is not sufficient. But if you can use these algorithms to basically create a broad beam using multiple antennas, okay, and then you will use all the 2 watts or 64 watts and you will be able to serve the users. Okay, right? So what am I saying? First step is happening at the transmitter side, wherein base station uses these broad beams, generates these broad beams using multiple antenna to broadcast these broadcast signals. Okay, right? So once that is done, then we'll move on to the next step and I'll teach you in the last class of this course. Okay, thank you.